Good morning. Welcome to the lecture. Another reminder about course evaluation. I think it ends next Tuesday, so we don't have a lot of time, and only like 10% of the students did the course evaluation for 451. At least it was a little bit better for 431, but not that great. So I appreciate if you can fill out the form. All right. Today I'm going to start talking about the last topic. So we only have two more lectures, today and Tuesday. And we're going to talk about graphs again. Yeah, seriously, yes. So we're going to talk about advanced topics in graphs. So we talked about graphs quite a lot already, but it's a very important topic in big data because a lot of basically data sets or data that we have out there can be formulated as a graph. For example, all social media networks like Facebook, LinkedIn, anything like that is like a graph. The web is a graph. So it's very important. So what we want to do in the next two lectures, I'm going to talk about some advanced topics. I'm going to introduce a graph processing framework. We haven't done that before. We talked about graphs, but we use a Spark and Hadoop to develop algorithms. We didn't talk about a specialized framework for graphs. That's the topic of today. And in the next session, we'll talk more about PageRank and basically attacks against PageRank, because we assume that the users are honest, but now we want to figure out what happens when somebody tries to manipulate the data structure in a way to fool the PageRank algorithm. We want to see how we can defend it against that and Google's ideas to basically fix the problem. That would be next session and last session. So if you remember, we talked about PageRank, the PageRank algorithm, and this was the Spark implementation. CS431 students did something like this for one of the assignments. Again, something similar to this for 451 students, but it was in Hadoop. So the idea was, okay, we needed two pieces of data. One is the adjacency list, and one is the PageRank vector, right? And in every iteration, we would join these two RDDs and perform some calculations, and that would give us a new PageRank vector, and we would repeat this until it converges. And if you remember, we said most graph algorithms are formulated like this, that we perform some local computations on a node, and then we basically pass some messages along the edges of the graph. For example, in PageRank, we calculate our PageRank score, and then we would distribute that amongst our neighbors. We pass scores to those neighbors, and then we repeat this process until we converge. And we saw that this way of solving the problem is very common in graph algorithms. What we want to do today is to see if we can make this faster. And the first thing that we will focus on is basically message passing along graph edges. So when we work with big data algorithms, one of the ideas that we repeatedly visited was partitioning. Right? We have data, we want to divide it up into partitions. And this is a very important thing when we work with graphs. Partitioning is very important. So let's talk about this a little bit. Let me explain first what it means and what are the common techniques. So hash partitioning is the default technique. So let me give you an example. Suppose that we have a graph, right? So it has a bunch of nodes. It's a huge graph. So I'm not showing everything obviously here. So what we want to do, and then there are obviously some edges here, right? When we say we want to partition, so you can imagine that, okay, all of the data is in a file, and every line of that file maybe is representing one of the nodes. Now you want to partition that file. How do we do that? So the job here is to assign every node like this to one of the partitions that we have. For example, we can have n partitions, and we want to see which partition every node should go to. And then we can start processing, right? So this is dividing data. So dividing data, when we work with graphs, is very tricky because the structure of the graph is very complex. And I will talk more about what is an efficient partitioning. But now let's see what happens with default hash partitioning. So hash partitioning says, okay, I have a bunch of objects and I want to assign them to partitions. And what I do, I hash every object, and that gives me a number, and that would be the partition number. For example, I hash this node and it tells me it's 2, so it goes to that partition. I hash this node here and the hash value is 1, so I assign it to that other partition. So what you can see happening here is that basically we are assigning these nodes randomly to the partitions, because the hash function is random. So when you hash it, it goes to one of those buckets randomly. Is that good? No, because we said we want, in a graph, you want to pass messages to your neighbors, right? If your neighbor is on a different partition, is in a different partition, it means that a different server is handling that partition, which means when I want to send some PageRank scores, for example, to that node, that involves network communication. For example, let's suppose that in this example, there's an edge between these two nodes, and this guy wants to send something to this guy. But this node is here, and the neighbor is here. These are two different servers, assuming that every partition is handled by a different worker node. So this means when I want to pass some partial scores, I need to send a network packet to that node, which lives on a different server. And that's problematic. So when you do hash partitioning, you are basically partitioning or assigning my neighbors to random buckets. So it's very likely that my neighbors are on other servers, which is really bad. Can we do something better? So these heuristics are really interesting. So the first one is web pages. So if the graph is a web graph, can we partition the graph in a more smarter way? Instead of just randomly assigning the nodes to partitions, let's do a better, more efficient assignment. And the idea is interesting. It says, hey, these are the web pages that I have. Again, a small example. So in hash partitioning, what happens? These nodes are assigned to random partitions, right? Different nodes, different partitions. But we know that, okay, for example, this node here is a neighbor of this node. So the urlu.ca web page has a link to ec.urlu.ca and also has a link to this one, right? So if you randomly assign these web pages, that would be bad. That would be what I explained before. But the idea that we have here is interesting. It says, do this. First, calculate the reverse of every domain, okay? So that this part comes first, and then the domain name, okay? So first the domain, and then the domain name. So it will be something like that. And then sort them. So when you sort them, this will happen. So it will be this order, right? Now it says, if you now partition it, if you just cut this file randomly from somewhere, let's say you say these ones in one partition and these ones are in the second partition. Simple example, so I have two partitions only. So remember, each of these URLs is a node on the web graph. So now what happened is that all these three URL websites went to the same partition. Obviously, there's one that we missed. I mean, assuming that we don't have much knowledge and we're just cutting, we can do even a more efficient way and just say, okay, no, we continue until the domain changes. So I assign these to a partition and the rest will be to another partition. Doesn't matter. The important thing here is that now we are not assigning stuff randomly, but based on the URL. And this heuristic assumes that when you do that, it's more likely that we have links between these web pages than a link from this page to this page, which is a different domain. So basically, if you have two .ca websites and one .com website, I ask you, if you want to bet on this, if you want to choose two websites that have a link to one another, which ones do you think they are? The two .ca website or one of the .ca and the .com website? You may say most probably the .ca websites. That's the idea. That's why we do reverse the URLs and then we sort them. This way we think when we sort them this way, we believe that there would be more links between these pages that go to the same partition. Again, it's a heuristic. It doesn't need to be absolutely correct, but if it increases the chance of neighbors going to the same partition, we win. Does it work? Let's look at some results. And let me know if you have any questions about how this works meanwhile. So this is the baseline. We have different techniques. This is a baseline. This is the running time. So lower is better. So baseline, which uses regular combiners. Okay, so it's done. This is the PageRank performance over web graph. So this uses regular combiners. If you remove regular combiners, the performance will be 18% worse. If you use in-mapper combiner, you gain around 15% compared to the baseline, which uses regular combiners. We have seen something like this before. And these ones use hash partitioning, meaning that the web pages are assigned randomly to partitions. But now if we use range partitioning, which is what I explained just now, we gain 60% performance over the baseline, which is fantastic. It's a great improvement. And all we have done, we did not increase resources. We did not change the algorithm. All we did, we assigned the web pages differently to the partitions. It's much smarter than a random assignment. And you can see that it performs much better because web pages that have more links to one another are more likely to go to the same partition, and that will reduce the amount of network traffic. Because if I want to send a message to a neighbor that lives on the same server, that will be like in-memory communication, which is super fast compared to sending a message to a node that's on a different server. That takes milliseconds because we need network traffic. Questions? All right, let's move on then. So that was the web page graph. How about other graphs, such as social networks? They're different, right? So the social network graph looks like this. Every node is a profile on Facebook, for example. Then links are like friendship between a node and another node. So this concept of the domain reverse URL sorting doesn't really apply to it. It's a different data structure. How can we do this? So this is, again, is a very interesting idea. How can we assign the nodes in a smart way to partitions so that we have a better chance of assigning neighbors to the same partition? Geographic location, exactly. So the idea is, so the example that I'm going to give you now is that, okay, suppose that I have two random profiles, both of them from Canada. and another random profile from, let's say, Italy. If you want to bet on two of these three people being friends with one another, which ones do you pick? The Canadian ones or one of the Canadian profiles and the Italian profile? Most likely the Canadian ones. We can even make it more specific. For example, if we have two people from Waterloo and one person from Vancouver, for example, or even a different country, what are the chances that two of these three people are friends? You would say probably the ones from Waterloo or the ones from the same country. The probability is higher. And what is this probability? This is a probability that there's an edge between these two nodes on the graph. So that's the probability of these two nodes being neighbors. So is this even true? So there was a study on this. This shows how much or how many links we have between profiles from different countries. Okay, so this is a heat map. So the X and Y axis are country names, so same basically ordering. And if like warmer colors like red and orange, it means there are more links between those two countries. And if it's a colder color like blue, it means there aren't many links between those two countries. From the first look, we immediately realized that this line has many squares with warm colors, so very strong relationships between those two countries. And what are those countries? So it's the country in itself, right? So because the ordering is the same. So the reason this line is warm is that it's the same country. It means that most links were between people in that country. And by the way, I think I forgot to say that this data is from Facebook. For example, if you look at Canada, probably the warmest color is this one, which is Canada, meaning that most links are between two profiles from Canada. Okay, so there are also some other relationships as well because of the geography and probably the countries that are closer to each other, things like that. But the important message is this line, which has like the highest scores. So it means that if we partition users based on their country or the region they're from, it's more likely that we assign neighbors to the same partition. Pretty interesting. Questions about this? So what we have done, just to recap, what we have done, we basically try to infer some property in that graph that suggests if we divide this graph based on that information, it's more likely we assign neighbors to the same partition. But the question is, how about graphs in general? You talked about very specific applications and used very specific properties in those graphs to come up with these ideas. But if it's a general graph that you don't know much about, what can we do? How can we do a better, more smart partitioning? Well, the answer is graphs in general look like this. And actually, partitioning a graph, a general graph, is an NP-hard problem. So not easy, okay? So all we can do is for specific graphs like web and social media, we can come up with heuristics. Again, those are not exact because it's NP-hard, but the heuristics work pretty okay. But in general, there's no solution. So another topic that we can revisit is reducing the cross-partition communication. So if partitioning is a challenge, can we at least try to reduce the amount of network traffic between different partitions? And this, what I'm going to explain next, is the industry solution to this problem. So what they do is, in order to reduce like cross-partition communication, which just slows down operation, they find these connecting nodes first. And there are heuristics for doing this, like graph coarsening and things like that. So they find nodes that if you remove them, the graph becomes partitioned. Okay. For example, here, this node has this property. So if you remove this node or the links it has to this other part of the graph, you can see that it breaks the graph, right? Because there's no other way to the left part of the graph except through that node. So you can imagine that, okay, we can divide these two into two partitions, but now the fundamental issue that we have is this. Computation inside each partition is very fast, because if I want to pass some message from this node to this node, super fast. It's on the same machine. So it's in-memory communication. But as soon as I want to send something across the partition from this node to this node, I need to rely on network to send a packet to the other server. And that will be extremely slow, orders of magnitude slower than within partition communication. So that's the root cause of the problem. And this is the solution. They say, let's replicate that connecting node in both partitions. Okay, so it is right now in the left partition. Let's replicate it so that we have another copy of it on the right partition as well. Now the two partitions are completely disconnected. These are like two independent graphs. The idea goes like this. It says you can iterate very fast within each partition. For example, if this is PageRank, you can run PageRank on this graph. So this is a single machine. So it's like there's one graph on a single machine. So that would be very fast. Everything is probably in memory or on at least the disk of the same machine, which is really fast. Same here. But you may say, wait a second, but this won't give you correct results because you don't pass any message between these two. For example, what happens to the PageRank scores that this part of the graph gets from this part of the graph? That's the whole purpose of PageRank. Okay, you're right. We cannot just independently run these as two separate graphs. What happens is we run fast asynchronous iterations on each partition, and then periodically we synchronize the two partitions. For example, this guy has some score, this guy has some score. So we try to synchronize so that we allow passage of the scores from one part of the graph to the other part of the graph. And that movement of a score happens through this node because this was a connecting node, right? So this is like a bridge between the two nodes. So as soon as we synchronize these, it will be fine. So what happens? What do you mean exactly here? Okay, what we can do is we can do 10 iterations independently on these two, and then we synchronize them. And then we do 10 more iterations on each partitions and then synchronize. So something like that. So we run independently and then periodically we synchronize the two partitions through the connecting node. Makes sense? So that's the idea. So this way we reduce the cross-partition communication. Instead of in every iteration we have to pass the scores, we don't do that for a bunch of iterations, and then we synchronize. Then we pass messages between the partitions to synchronize them. And that takes us to the next part of this lecture. Are there any questions about what we talked about? In the next part, I'm going to introduce a new graph processing framework. So it's a different a new big data system, specifically designed for processing graphs. Should we move on? All right, so I'm going to introduce a new framework, and I'll have a small demo at the end of the lecture. Hopefully it will be fun. All right, so graph processing frameworks. What happened? We had Hadoop, we had the Spark. People realized that we are developing a lot of graph processing algorithms. Why not have a framework that was specifically designed and optimized for processing graphs? Because it's a very common data structure. It makes sense to have its own system. Again, Google. Google designed something called Pregel, and it was, I believe it was the first graph processing framework. And like other software coming from Google, they published a paper, and then an equivalent open source version was developed, and it became again one of the top Apache projects. So we have Apache Giraffe, which is the open source implementation of Pregel, pretty much. It's based on Pregel, and it works on top of Hadoop. So that's nice. So we don't need a new cluster. It works on top of Hadoop, and it's basically part of the Hadoop ecosystem. So another animal in the zoo. Okay, giraffe now. And like always, whenever people do something in Hadoop, Spark says we can do that too. So they also design a system specifically for graph called Spark GraphX. Today, I'm going to talk about giraffe. So giraffe, another animal in the zoo. It's widely used, especially in companies that work with social networks, such as Facebook. Its performance is awesome for graph processing stuff. For example, I remember one study where Facebook did some processing on 1 trillion edges on 200 machines in 4 minutes on Giraffe. So as far as I know, it is still used at Facebook. As I said, it runs on top of existing Hadoop clusters, and it's very fast for iterative calculations. And the trick that it does to enable fast iterations is that Hadoop, in Hadoop, everything goes to disk. That's why it's so slow. So the way it works at the high level is like this. So we have a Hadoop cluster. Giraffe hijacks mappers, and it does its own calculation inside the mappers, and everything is done in memory, actually. Although the underlying system is map reduced, but first of all, it only uses maps. It does not use reduce, so we don't have shuffling. So it hijacks basically the computation capability of mappers, and it runs its own algorithm on those nodes. And it tries to keep everything in memory, and that's why it's so fast. Giraffe is based on a specific programming model called Bulk Synchronous Parallel Programming Model, or BSP for short. How does it work? It says you should program from the point of view of a node. So you think you are one of these nodes in this graph, and you have to program from that point of view. So basically, if you're this node, what happens is that in the current iteration, you receive some messages from your neighbor, from the nodes that have a link to you. So this can be PageRank. So these guys will give you some partial PageRank score. And then in the next iteration, what you do is that you do some calculations inside this node, and then you pass messages to your neighbors. And that would be the partial MapReduce score, sorry, PageRank score that you give to your neighbors. And then when you write something from the point of view of a node, you can basically run this on all nodes simultaneously. So every node does the same thing. That was not a special node. Every node does this, that it receives some partial scores and it gives some scores to its neighbors. So every vertex or every node requires to know its own value and the outgoing edges. So I know that my PageRank score is this. And if I know my neighbors, I pass this message to my neighbors. And everybody can do this, and the algorithm works just fine. So let's talk more about this BSP programming model. So the way it works is like this. So we have 4 partitions, P1 to P4, running on, let's say, 4 servers. Inside each partition, there are thousands or millions of nodes of the graph that we are processing. So first we do some computation depending on the algorithm that we are working with, right? So if it's PageRank, this is what we have to do to come up with the score, for example. And then when we are done, and as you can see, every partition or every server will be done at a different time because the processing power might be different, or the partition that was assigned to that server might be bigger. So they have different termination time. And then in the next phase, we need communication. So we said we do 2 things. We compute locally on every node, and we pass messages to neighbors. So in this phase, we pass messages to neighbors. So this is basically PageRank score going from some nodes in this partition to some nodes in this partition. And the same for all partitions. So all of them exchange messages. And then there's a synchronization barrier. So this barrier prevents servers from going to the next step. It says, hey, we need to wait until everybody is done in this round. Then we can start the next round. So there's a barrier. And these rounds or iterations are called superstep in Giraffe. So we start from superstep 0 or 1, and then we go on to superstep 2 when everybody is done with computation and communication. So that's it, basically. That's the bulk synchronous parallel. Nothing very crazy, but fancy name again. As you can imagine, this message exchange is very heavy. It's heavy communication between servers at the end of every super step. So we have to be careful with this. So if Giraffe just wants to do this, the performance will not be great. So there's yet another trick that solves the problem for us. Very interesting. It says when we process graphs, in many cases, in a particular iteration, a node may not have anything new to tell to its neighbors. Like in the shortest path algorithm, if you imagine that, in many steps, the shortest path does not change to a particular node. So there's no need for that node to inform its neighbors about the same information every time in every iteration. So if I told my neighbor in the last iteration that my shortest path to you is 7, and if in the next iteration that information does not change, why should I tell the neighbor again that my shortest path to you is 7? That's stupid. So we should stop those messages. We should stop those repetitive messages that have no value. And that's the idea that the Giraffe implements to significantly reduce the amount of messages we need to communicate between different partitions at the end of every super step. So a node is in two states, either active or inactive. When an active node doesn't have anything else to do, when the information it's going to tell its neighbor is the same as the last iteration, it says, I won't do that. I will go to this inactive state. I will not send any messages. If it receives some new messages, and for example, the shortest path is updated, now my shortest path to my neighbor is 5 instead of 7. Now I should inform my neighbor again. So in that case, I wake up, I send messages again. When I'm done and I don't have anything new, I go back to sleep. And the algorithm actually terminates when every node goes to inactive mode, because when no one has anything new to say, we will remain in that state forever. So it's done. Let me give you an example. I have a graph here with 4 nodes. Again, big data examples. So 4 nodes, and there's a value in each node, 1, 2, 6, 3. In my stupid example, I have 2 partitions. Each has 2 nodes only. And the arrows that you see here, the orange arrows, are the links in this directed graph. For example, this guy has a link to this guy and also the other way, but here this guy has a node to this one only. Also, this one has a link to this one, so on and so forth. Okay. The algorithm I want to run is this. I want to find the largest value in this graph, which is 6. It's a very simple example, kind of stupid, but it tells you how BSP works. Okay. Let's see how this goes. The idea is like this. Every node informs its neighbors about the largest value that it has seen already. And hopefully, if we repeat this process a few times, everybody will find that value. So we will find, okay, so now we converge and the value is this. Let's see how it goes. In the first iteration, so let me take a step back. So we are in super step 0. In the first super step, every node is active. I'm showing active node with orange. The ones that don't have anything to do will be shown with blue later on. But in the first step, it's a fresh start. Everybody has something to tell or gossip with the neighbors. So, for example, here, there's a link between this one and this one. So this guy will send a message to this one and says, hey, the largest value that I'm aware of is 6. And then this guy says, oh, thank you. So the value that I knew was 3, so I will update my value. Thank you. And this one, similar to that, it sends a message to this one, says, the largest value that I'm aware of is 3. So always think about the previous step, not the new one. It doesn't know about this beforehand. So it says, okay, the largest value that I'm aware of is 3, sends this message to 6. It says, thank you, but my value is already bigger. So, and then similarly, see, so these arrows, the blue arrows, are indicating the messages that we are sending. For example, there's an arrow from here to here, so there's a link. So this guy should inform this node. So it sends a message to 1 and it updates the value. So it says, oh, thank you, my value was 1, so I update my value to 6. And then similarly here, 2 only has 1 incoming link, and that's from 1. So 1 informs 2 and says, thank you, my value is already bigger. So if you think, okay, and we are done. Now, look at the values. This one was 3, became 6. This one was 6, it is still 6. This one was 2, still 2. It was 1, it is 6. So 2 of these nodes changed in the previous super step. So they have something new to tell their neighbors. But these 2 didn't change in the last round. So there's no point this guy tells its neighbor again that the largest value is 6. But it already told them. Right? So we can eliminate those messages. And that's the idea, that they can go to this halted state. So these 2 halt. They say, okay, we don't have anything new to tell our neighbors. We move on to the next round. As you can see, there is no blue arrow coming out of these nodes because they do not participate in messaging in this round. This guy is active. It informs its neighbors. The only neighbor is this guy. It says, hey, the largest value I have found is 6. And it says, shut up, I told you that value. So there's still nothing useful for this guy. And then the only useful thing is this one. This guy says, hey, I now have a new value and it's 6. It passes that value to 2. 2 says, hey, thank you. I update my value. And now, again, if you check, this one is still 6. It was 6, it's still 6. And this one is 6. So we can see these 3 nodes go to sleep. This one is the only one that's active still, because it was 2, it's now 6. Now, in the last super step, this guy will send this message to its neighbor. So the neighbors are this one and this one, right? This one says, hey, shut up, I told you that. And say this one, same thing. Say, I have like idiot neighbors, keep telling me my own value. So again, it ignores it. And this one was 6. It is still 6, obviously. So it goes to sleep or to halt mode. So all of them are now in a sleep mode. So we are done. So the algorithm has converged. Okay, got a question. How do you know if your neighbor is inactive or if there is network latency slowing down the message? So the master node that takes care of that, the barrier, will have a timeout, something like that, right? So the master knows that that node is alive, but it's not sending messages. So it knows about this. So it's okay. So that guy is fine. And in practice, remember that there are many nodes in every partition. In my stupid example, there are only 2. So almost in every iteration except the very last ones, every server has some messages to send to other servers, because there are millions of nodes in every partition. And if at least one of them is active, it has a message to send. Okay. But yes, in the very last rounds, maybe we don't have a lot of messages, but the master node knows about what's going on. So that's basically it. So remember that if a node is in inactive mode, it does not send out any messages, but it receives messages. Sure, I'm in sleep. The system will say, hey, wake up, there are some messages for you. I wake up, I receive messages. If I have something new, I will stay awake. Otherwise, I go back to sleep. For example, here, this guy receives messages, but it is still in the sleep mode. Again, here, it receives something where it figures out there's nothing new. So it is still in the sleep mode. So that's how it works. Other questions? While you're thinking about your questions, let me go over the code for the same thing. So you can see it's pretty simple. My algorithm was simple, but even if my algorithm is more complex like PageRank, it is pretty much like this. That's the beauty of it. So in Giraffe, the only function you need to define is compute. Like in MapReduce, where you have to define map and reduce. Here, the only one that you need to define is this one, compute. So it takes a bunch of parameters, for example, the vertex. So which vertex we're talking about right now, which is a complex data structure like this, and the messages that this vertex or node received. So it's pretty simple. Again, this is a vertex-centric model. So you have to think you are one of the nodes. You forget about the rest of the graph. So what you should do here is that from my point of view, I receive some messages and I have some neighbors. If the value changes, I will inform my neighbors. That's all I do. I don't care about the rest of the graph. So we have a Boolean flag that's false. I go through all of the messages that I received. I compare them with my current value. If the message value is higher than my own value, I update my value. So if my value was 3, I now update it to 6. And I set the flag to true. After that, I check if we are in the first super step, which means everybody is active, or the state has changed. So my value was 3 and now it's 6. I send a message to all of my neighbors and I inform them about my new value. It was 3, now it's 6. I inform them. And this send message to all edges. This is like a built-in function in Giraffe. So you can use it. So you can see it provides these interesting tools. You don't need to do this yourself. So you just need to call this function. And then after that, it votes to halt. said, okay, for now I'm done. I don't have anything else to do. Unless this flag becomes true later on, I will be in the sleep mode. And the flag becomes true only if I get a message that contains a value that's bigger than my current value. So the beauty of Apache Giraffe is that we don't need locks, semaphores. So that's all you implement. Do you see a lock? No. So you don't have to worry about that. The idea of going to sleep makes message passing very efficient. So we only send messages when it's necessary. And everything is stateful. Everything is in memory. That's why it performs so good. You have the option of persistent storage. Sometimes your algorithm is very heavy or it's running on a huge data set. In that case, iterations may take time and you may need many iterations, so it may take a day. So if something goes wrong, because everything is in memory, you lose the data if something crashes while your program is running. So if you are in that case where the algorithm will run for hours, it makes sense to add some checkpoints in your program. What checkpoints do, they take a snapshot of the current state and store it to disk. If there is a problem, you can restore from that iteration that you checkpointed. Okay? But it's not necessary. Like here, I didn't define anything like that. I just say, hey, run this. If it crashes in the middle, I have to run again from the beginning. It's an optional feature. It mostly makes sense when you have a lot of data and it takes time. So the Giraffe architecture is like this. It has a master node and a bunch of worker nodes. So the master takes care of synchronization. We told you about the barrier. So that's the master node that takes care of this. It makes sure that workers don't jump to the next state until everybody is done. And it assigns partitions to workers before the first super step. What workers do, they perform computation and message passing, all of that. And finally, we have Zookeeper. Zookeeper, as we said, this is a highly available lock mechanism in Hadoop ecosystem. What it does, as I told you, this is running on top of MapReduce. All nodes are the same. There's no master. We have the master of MapReduce, but that's a different thing, right? For Giraffe, I just have a bunch of nodes. I just have a bunch of worker nodes. So what happens at the beginning, workers use Zookeeper to elect one of the nodes as the master. So say, okay, you be the master for this application, and the rest of the nodes will be worker nodes. So that's the use of Zookeeper in this process. And after that, we have a master, we can start. And again, this is the life cycle. I think we talked about this, but let's look at this quickly again. So we have the loading phase. This is when we read vertex data from probably Hadoop file system, and we load it into memory. Okay. So because it's based on MapReduce, so we have all of the stuff like input format and things like that CS451 students are familiar with. So we have all of that. So we load the data, okay? And now we start computation. So we start computation, and then all workers finish message exchange. So we are at that barrier right now. And then we check to see if everybody is in halt mode. If everybody is sleeping, we are done. And we basically move on to the final stage. Otherwise, we move on to the next super step, and the compute function is called again. And the same process repeats over and over again until everybody halts. In that case, we move on and we print the stuffs or we dump the output to HDFS. Again, we have stuff like output format, all of those things that Hadoop has. Okay. So let's look at another example here, and then I finish with the demo. I think that's cleaner. So let me show you a more realistic example. Okay, the finding largest value was kind of stupid. Let's talk about the single source shortest path algorithm. We talked about this before a little bit. We said Dijkstra doesn't work when we have a lot of nodes because we cannot load everything in memory and things like that. So how does a Giraffe run this? Okay, in my simple example, again, this is pretty simple. I have 4 partitions. These are the green boxes. And I have a bunch of nodes. I think I have 2 in each box, so 8 nodes in general. And in total, sorry. And there is some weight on each edge, and that's the cost of going from this node to this node. And we want to find the shortest path, or better to say shortest score, or the smallest score from a source node, in this case it's A, to all other nodes. So we want to find the shortest path to all other nodes. How does it work? It works like this. At the beginning, we initialize the graph like this, if you remember, that the score of the source node is 0 because there's no cost. We are already there. And the cost of reaching other nodes is infinity for now because we haven't seen them yet. So we are in super step 0. What happens? The active nodes, which is this guy only, the rest of them are in infinity. So they are in halt mode for now. This guy has something to tell other neighbors. Say my score is 0, so the cost to reach to you is 1, and the cost to reach to you is 2. So it passes 1 and 2 to these nodes. In the next super step, we are done with that super step. We move on to the next super step. These 2 become active because they used to be infinity. Now they are some other values. So they have to inform their neighbors. So they do the same thing. They say, hey, 1 plus 2, you're now 3. 1 plus 3, you are 4, so on and so forth. So they inform their neighbors. So those neighbors become active now because their value changed, and they go back to sleep because in this particular example that I'm showing you here, there's no new message for them. So their value is still 1 and 2, so they are still in the sleep mode. They go back to sleep. And then same thing happens again. So they inform their neighbors, and these guys become active. In this case, they don't have any neighbors, so they don't have anything to do, and they don't receive any new message. So they also halt, and the algorithm converges, and that would be the shortest path, or the score for the shortest path from the source node to all other nodes, using the BSP idea and Giraffe implementation. Any questions? And this is the code. So again, what we do here for the shortest path algorithm, we go through the messages that we have received, and we pick the minimum one. So for example, here, if this guy claimed that my path to you is 3 plus 5, which is 8, and this one says 4 plus 2, which is 6. So this guy receives 8 and 6. So it receives 2 messages. One is 8, one is 6. It takes the minimum. So it takes the minimum and it sets its, it finds the minimum score that it gets from the messages, and it compares that with its own value. If it's smaller than its own value, then it needs to update it. And in this case, it sets the value, and it basically loops over all of the edges. And remember that we cannot use that function that I told you in the previous algorithm, because in the previous algorithm, the largest number example, we were sending the same message to all of the neighbors. Because, for example, I knew that the largest value is 6, and I would tell, hey, 6, 6, 6 to everybody. But here, in the shortest path, the message I'm sending to my neighbors depend on the weight to that neighbor. So it's not the same value. I tell this guy 4, I tell this guy 6, because the edges are different. So we need to loop through the edges, and we add my value plus the weight, sorry, yes, my value, the minimum that I found, plus the cost of going from this node to the neighbor node, and I send that message to that node, and I need to loop through, and I do again send message is one of the given functions, and I use it to inform my neighbors that I have found a shorter path, and I go back to sleep. Again, you can see it's a very nice and intelligent way of working with graph. So if you compare this with what we implemented in Hadoop and Spark, you can see that this is much cleaner because the framework was designed for such data structure. So you don't need to take care of nodes and edges, create RDDs for them, take care of them. No, it's done behind the scene. So that's nice. And you just focus on what happens on every node. Time for the demo. Let me know if you have any questions. Okay, that was really last slide. Good. So now let's move on to the example that we have. All right. Can you see my screen? Yes, no, can you see the screen? Thank you. So, so the nice thing about Giraffe is that if you have a MapReduce cluster, a Hadoop cluster, you can simply add Giraffe as well without even having sudo access. I'm using the course account, but it doesn't have sudo access in on data side. So what I've done, I simply copied this Giraffe directory. That's all I needed to do to install it. And this, I just downloaded it. So this is the Giraffe Apache Giraffe project. So basically you copy it somewhere, and you need to adjust some settings inside it so that it finds Hadoop, obviously. But that's all, and you don't even need sudo access. And it comes with a bunch of examples. You can investigate like what's inside this example. I'm going to run one of those examples now. So the way you run Giraffe is pretty much like Hadoop. So I put it in this bash script so you can see that it's actually Hadoop that you run. So Hadoop, and then you run an example. Okay, so this is the one that I'm running is this example here. So simple shortest path computation. But the difference is the way you tell it that this is Giraffe, not a regular Hadoop program is this. And then the rest is the same. For example, you have some input basically format the input file, and then output format and output file, things like that, like exactly like Hadoop. And when I run it, you'll see that it's like it launches a Hadoop program and like something like that. So I have it in this example. Let me show you actually what I have here. So this is the shortest path computation. So it's if I can find it. Examples, and then here we have source, we have main, we have Java. Okay, and then it was simple shortest path computation. So let's have a look at this. So at the beginning, you can see it's just Hadoop stuffs, as you can see. But we obviously import some of the Giraffe libraries, but you can see that you also import like Hadoop stuff, like a regular Hadoop program. And then we have a main class. And then we should find for that compute function. There you go. This is basically your program. The rest of it is pretty much boilerplate code. So it's pretty much like what I reviewed in the very last slide. So we calculate basically the minimum distance, and we loop through all of the messages that we received. If it's less than what we have already found, we set the value. Then we loop again through all of the outgoing edges, and I call the send message function, and I inform my neighbors about the new thing that I found. So it's Hadoop and Java basically. But the function that you overwrite is not map and reduce, but rather it's this public void compute. All right, so even if you want to calculate something even more complex, such as PageRank, it will be pretty much these many lines, because all you need to do is calculate your PageRank score, and then you pass it to your neighbors. It's exactly the same, right? And there are some examples. If you're interested, you can download it and have a look at those examples. So the input file is already on Hadoop file system. So Hadoop file system, show me the, I think it was tinygraph dot, was it text? Let's test. Yes. So this is basically the node ID. So I have, again, a stupid example. I don't want to wait for an hour, so I test it on a small graph. So 5 nodes, 0, 1, 2, 3, 4, and then here there's a list. The list is telling us what neighbors we have and what is this the cost to reach to that neighbor. So 0 has a link to 1 and the cost is 1. 0 has a link to 3 and the cost is 3. 1 has a link to 0 and the cost is 1, so on and so forth. Okay. And because I ran this, I'm going to run this and then it find the shortest path for us. And I believe in my program, 1 is the source node. So so let me see, the output goes to this shortest path directory on Hadoop. So because I ran it last night to test it, I need to remove it from Hadoop file system first before I run it. System dash. I don't remember if this works or not. Directories are a little bit tricky. So let's hope this works. Okay, it moved to trash. Perfect. Now I run my bash script that has that command. Let's see what happens. As you can see, it's pretty much like MapReduce, right? We start this, it's launching something, and then it says, waiting for resources. Job will start only when it gets all 2 mappers. So it only needs 2 mappers in this case. It's a small graph. So when it can hijack those resources, it starts computing. Okay, it finished successfully. Don't be confused by the red failure thing. This is my editor highlighting different keywords. It finished with no problem. So now to test, the output also goes to that shortest path directory. Let's see if it's there. So I deleted it before, so I can now ls to see if it's there. Cool. So as you can see, it produces part files. It's Hadoop, right? So I can do shortest path slash, what is it? Part something. I'm so lazy. Okay. There you go. So this is the shortest path. Let me open the file. I also have a copy of it on the local disk. See if it makes sense. I told you that in my program, I set the source node to be 1, not 0. So the cost to reach 0, sorry, the cost to reach 1 is 0 because we are there. The cost to reach 0 is 1 because 1 has a link to 0. And the cost is 1, so that's the shortest one. How about 2? So 1 also has a link to 2, and the cost is 2. That's the shortest path. 3 is 1. because it also has a link to 3 and the cost is 1 and that's the shortest one. 4 will be more tricky. 4 is 5. So 1 has a link to 0, 2, and 3. And let's see which of those has a link to 4. This one doesn't have a link to 4. Both of these have links to 4. But the cost is the same. So it's 4 to go from 2 or 3 to 4. But the cost to go to 3 is lower than this, right? So we go to 3 first with the cost of 1, and then from 3 we go to 4 with cost of 4, so that would be 5. So it's correct. So that's nice. If you have access to a Hadoop cluster, you can simply install Giraffe without sudo access, and you can just run anything you want. And as I said, there are many examples that you can look at. It has things that you learned in this course, like PageRank and some other algorithms. So it has simple PageRank computation if you want to have a look at. This is the one that I just ran, and some other examples. So you can see there are a lot of PageRank related stuffs because it's a famous algorithm. So it's pretty cool. All right, questions? All right, so let me stop recording. Thanks for attending the lecture. Feel free to leave. I will be around.